for spring-supported beams. And so not only are we going to talk about Winkler foundations, but we are also going to look at discrete springs. So this can be a linear spring at a specific node or a rotational spring at a specific node. So we'll look at all of that in this lecture. All right. Pick a color. So we'll start by talking about the Winkler foundation. And remember from before, right, we defined the Winkler foundation stiffness. Oops, that is not the pencil thickness I needed. All right. We defined that Winkler foundation stiffness K as the force per unit deflection per unit length of the beam. All right, and we call that the Winkler foundation modulus. And then also recall from our intro to finite element analysis lecture where we set all this stuff up through virtual work, etc. We defined a generalized displacement expression in matrix form, where v of x was equal to the row vector 1x, x squared, x cubed, times the coefficient matrix B times the generalized displacements. And that's in lecture 10. If you want to revisit. For the Winkler foundation, our strain energy increment will now look like this. So we're going to have our Winkler modulus divided by 2 out front times the integral from 0 to L. And then we're going to have that displacement expression transposed times the displacement expression. So writing this out, expanding it a bit, it's going to look like this. So we'd have the delta transpose times the B matrix transposed times turning that row vector into a column vector. And then the regular form. If we were to integrate all of that, we would end up with expression for strain energy is equal to the Winkler modulus K over 840 times the generalized displacement matrix transposed times the coefficient matrix shown here which my notes say, all right, so I guess that makes sense. So then in my notes, I am just abbreviating this matrix as KW for future reference. And then that will be multiplied by our generalized displacement matrix, which I'll write out here. So displacement at node 1, and then theta 1L, displacement at 2, and theta 2L. So that's just your delta matrix there. All right, so now taking the virtual work, right, as the increment delta comes into play, we have k over 840 times, in parentheses, our lowercase delta, capital delta transposed, times that kW coefficient matrix, times delta, plus delta transpose times kW times lowercase delta, capital delta. Now simplifying this, we get k over 420 times lowercase delta, capital delta transpose times kW times delta. Then applying the conditions for equilibrium, right, where the difference between internal strain energy and external work is 0. We end up with this expression where the first term represents the beam stiffness relationship. All right, so this should look familiar. And the second term represents the Winkler foundation relationship. And that reminds me that I have yet to assign homework on finite element analysis, so look for something to be posted later today. All right, so now we've set up our equation that we can use for Winkler foundation applications. We will come back to that and look at an actual example where we use this. Now I want to talk about what to do if we have discrete springs at nodes or concentrated springs at nodes. So first of all, we're all familiar with linear springs. Right, where F equals Kx, and K represents the force per unit deflection. Now we're going to introduce the concept of a rotational spring. This may be new, may not be new, depending on what you've seen in other classes. But it's a similar relationship between moment and rotation, where moment is equal to, we use the Greek letter eta, which is like a fancy N with a long tail, times theta. And eta represents the moment per unit rotation. All right, and in our finite element modeling that we are doing in this class, as you know, we've been dividing the moment values by L to normalize the units in that force matrix, right? And we've been multiplying the rotations by L to normalize the units in the displacement matrix. So we have M over L is equal to eta over L squared times theta L. All right, so now in the full equation, for a single element, it would look like this. EI over L cubed, and this is going to be a 4x4 matrix. So first column will have 12 plus, and we're referring to this sketch up here, where every node has a linear spring and a rotational spring. All right, so just think of them as potential spring locations. So in the first column, we'll have 12 plus K1 L cubed over EI, 6, negative 12, 6. In the second column, we'll have 6, 4 plus eta 1 times L over EI, and then negative 6 and 2. In the third column, we have negative 12, negative 6, 12 plus K2 L cubed over EI, and negative 6. Fourth column, 6, 2, negative 6, and 4 plus eta 2 L over EI. And that will be multiplied by V1 theta 1L, V2 theta 2L, to equal the external nodal forces. F1 M1 over L, F2 M2 over L. So it's these diagonal terms where the spring stiffness will get added into our beam stiffness relationship. So I'll just do a quick setup on this example to demonstrate. We're not gonna, oh, actually, no, I take that back. We will do the whole example. All right, we're gonna solve this whole beam. That's great. I thought we were gonna do a setup and then a different example, but it's easier to just do the whole thing. All right, so let's call this spring at node 2. We'll call that stiffness K2. So we have a single element beam, fixed end at the left. Free end has a spring support, so I don't know if it really still counts as a free end, but in our finite element analysis, we will be treating it as a free end with no external forces applied, all right? Because we're going to consider the spring as internal to the system, right? That's what we did up here. We're building the spring force into our stiffness matrix, right? So I'm gonna say for convenience, let's express K2 in terms of EI and L. So we'll call it's equal to some constant alpha times EI over L cubed. All right, and when we get to actually solving the problem, we're going to assume a value for alpha. In your homework or on an exam, you would be given a value for alpha, okay? All right, so we'll set up our equation. We have EI over L cubed times, oops. There we go. First column, we have 12, 6, negative 12, and 6. So we don't add anything to that node 1, column 1 value because there's no spring at node 1. Second column associated with the rotation at node 1. No rotational spring, so this is going to be business as usual. 6, 4, negative 6, and 2. Now the third column is the one associated with the vertical displacement at node 2, which is what will be affected by this linear spring. So we're going to have negative 12, negative 6, and then 12 plus alpha, and then negative 6. And then in the last column, it's going to be business as usual because there's no rotational spring at node 2. So 6, 2, negative 6, and 4. All right, and then we have our displacements. Go ahead and apply the boundary conditions, right? With a fixed support at node 1, we know that V1 and theta 1L are 0, right? Since those are associated with the first two columns, we will eliminate them from our analysis. And then on the right side of the equation, we'll list our forces and then make a note of what we know and don't know there. All right, so at node 1, fixed support, we don't know those reaction forces, M1 and F1. At node 2, we treat it as a free end even though there's a spring there. We do not know, or I should say we do know that there is no applied external force or moment there. We're treating that spring force as internal to the system. So F2 and M2 are equal to 0. And then we have a distributed load to think about. So we have to include that extra vector that we looked at last time. So that's going to be a QL over 12 times, we have 6, 1, 6, and negative 1. All right, so I'm going to make a note here, all right? In this example, we just have one element, but if you were to have multiple elements, you do not want to double that alpha term, all right? Just count it once per node. So that's just an important thing to remember. I'm going to note it down here. All right, and then the other note I'll add on this is that the force in the spring comes from this term. So after we solve for the unknowns here, we'll go back to this equation in row 3 to find the force in that spring.
So if we had a beam with multiple elements and the spring was in the middle, we would add, so we do 12 plus alpha when we do the combination of the matrix, only one alpha, or?
In the overlay, it should only show up once in the overlay. Okay. So yeah, so I'll I'll add that clarification.
In the overlay, I should say.
Once per, only once in the overlay. Or what did I say? Add once. In the overlay,
That makes sense.
yeah. All right, so is it pretty clear that, why we're separating out the spring force, the distributed load forces, and then these guys are always just going to be discrete external forces, either reactions or applied? Is that clear? Yes.
This is about the distributed load.
Okay.
The moment, isn't it QL squared over 12? As
Yes.
what you want, so is that
Um,
one supposed to, it's not, I don't really know what I'm asking.
That's okay. No, I think I know what you're getting at. You're correct. It is QL squared over 12, right? So that's what we wrote back in the last lecture, right?
At the bottom of
Here.
the first page on lecture 13.
Yep, QL squared over 12, exactly. But remember, we are dividing everything by L in that row, right? So that's why we end up with the QL, so that we have the same units. We have consistent units here, here, and here. So that's why we multiply our rotations by L and divide the moments by L.
Okay.
Yeah. Yeah, it's some fancy tricks to make this digestible by hand, right? A computer program wouldn't necessarily do it that way, right? But in order to make these solvable by hand, that's what we do. All right, so first partition, we want the rows that have known forces, so that would be rows 3 and 4. And here's where I will add that we're going to assume a value for alpha for this example. All right, so we'll take EI over L cubed times just the 4 values that we have in that first partition. So that'll be 14, that's our 12 plus 2, negative 6, and then negative 6 and 4 in the second column. This will get multiplied by the non-zero displacements, V2 and theta 2L, and set equal to our known forces. So on the right side, it's going to be 0 and 0 minus QL over 12 times 6 and negative 1. Solving for our displacements, we would get negative QL to the 4th over 120 EI times 9 and 11. So these results would be exact for those locations, the nodes, right? Then the second partition, we'll go back and use the remaining rows. So we're gonna have, I'm gonna bring, all right, so we're gonna have our stiffness matrix times our displacements that we now know, right, V2 and theta 2L. So I'm gonna bring this QL to the 4th term out front. So we have QL to the fourth over 120 EI times EI over L cubed. And our second partition is the first two rows of columns 3 and 4. So negative 12, negative 6, 6 and 2. And then we have 9 and 11 for the rest of our displacements. And that's equal to the unknown reaction forces, F1 and M1 over L, minus QL times 6 and 1. Now solving for F and M, we get QL over 60 times 51 and 21. So again, this is exact for those reactions at node 1.
Why isn't QL divided by 12 right there?
After,
In partition to like the second term.
oh, thank you. I accidentally omitted that. Yep, good catch. Okay. All right, so now that we have all the nodal results, we can go and find the force, calculate the force in that spring at node 2. So say the force in the spring, we know that expression is going to be F equals to K2 times the displacement at node 2. Now we know F2 and V2, or excuse me, we know K2 and V2, right? So we'll look for that force F2. So that's going to be 2 EI over L cubed. That's our K2 times QL, it'll be a negative QL to the fourth over 120 EI times 9. Which gives us 18, negative 18 QL over 120. So the negative value in that expression, right, is consistent with, it comes from the negative in our deflection, right? So the negative means it's moving downward, right, which means the force will be in compression in that spring. So that makes sense intuitively, right? When we go and interpret all of these results onto a final free body diagram, we have to think about what that means with respect to the beam. So we'll have our reactions at node 1. That's 17 over 20 times QL. And then the moment is 7 over 20 times QL squared. We have the applied load. We don't want to forget about that. All right, that's Q, length is L. So since the spring is in compression, it's going to be acting upward on the beam. So that fraction 18 over 120 reduces to 3 over 20. All right, so it's just going to be interpreted as a positive force, F2, when acting on the beam. And then always want to make sure that you verify equilibrium. So for a beam, that just means summing forces in y and summing moments about a point. So usually the vertical summation is pretty straightforward. Sometimes you can just eyeball it and say, yeah, you're good. In this case, you can pretty much eyeball it, right? Sum of moments is less obvious, so I do always look to see this equation fully checked. So we have our moment at the left plus, if we sum moments about 1, then we just have the spring force with a moment arm of L, and then distributed load is going to be magnitude of QL times a moment arm of L over 2. And that does check out. Okay. Questions? Okay.
So why did we start our assumption of the spring being internal to the system, but then we're looking for a force as if it was external to the system?
In order to solve the finite element, using the finite element approach, since we build that spring stiffness into our stiffness equation, our stiffness matrix, right? Since we build that coefficient into the K matrix for the beam stiffness, then we're essentially treating it as an internal force.
Okay.
Yeah.
Yeah.
Any other questions? Okay. Well, so a few minutes left. I'll start talking about this example. We'll probably have to finish a few comments on it next time, but here we have the elastic foundation, right? And we're looking at a beam with 2 elements and a point load at the center. With 2 elements, we would just assemble the overlaid matrix equation to get the whole system represented, right, as we did before, except now you have the Winkler matrix. So if we go back to page 1 of today's lecture, right, we had this equation for a single element. We're just taking that for 2 elements now and overlaying them at the common node. So we would be seeing, right, this would be the matrix for node 1, or element 1, and the matrix for element 2 overlaid. All right, so the 2 elements overlaid there. Now, in order to proceed with this solution, we need to be able to sum these 2 matrices together, right? And so that means we need to get creative with these terms out front so that we can do that and just have numbers to deal with our matrix math. So the steps that I have are kind of started. Let's see. So the first step, I'm going to skip down here. All right, we want to multiply both sides of the equation by L cubed over EI. All right, so we do that. looking at the left side of the equation, all right, that would go here. We would eliminate the term in front of our K matrix, and then in front of our Winkler matrix, let's see what that does. So if we're given this information that beta L is equal to 1 and capital L representing the length of the beam is 2 times lowercase l, which represents the length of one element. So I'm going to note here that this would be given information. So then, going back to this step up here where we pre-multiply this whole left side by L cubed over EI, that is going to factor into this right here. All right, so noting that, remember, we defined beta to the fourth as being equal to K over 4 EI. So then it follows that beta L, that product to the fourth, would be K times capital L to the fourth over 4 EI. And since beta L is equal to 1, then beta L to the fourth will be equal to 1. All right. So then going back to this, all right, taking L cubed over EI times KL over 420, we get KL to the fourth over 420 EI. Substituting in L, capital L equals 2L. So that'll be our second step here. All right. Then we can work this through, factor out this term, K capital L to the fourth over 4 EI, replace it with beta L to the fourth. All right. Replace that with 1, and then we get ourselves to just a number to put in front of that Winkler foundation matrix. All right, so that was perfect timing because that is a good stopping point where we are now all set up to proceed with the numeric solution, which we will wrap up on Monday. So, any questions? All right, well, thank you all for your attention. Keep an eye out for